Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So this is part 14. So on distributed forces, and we apply hydrostatic uh, pressure principle as well as the principle on buoyancy by Archimedes. And this part will end up to part 15. So the theory behind hydrostatic pressure as well as for buoyancy laws were already presented in the preceding videos. So I hope that you can continue with the applications of those principles in the following problems to follow, and hope you can follow also the explanation and the solutions.
Level 76. A zero point 0.5 by zero point 0.8 meter gate AB is located at the bottom of a tank filled with water. The gate is hinged along its top edge A and rests on a frictionless top at B. Determine the minimum tension required in cable BCD to open the gate. So here is the given figure, and this is zero point 0.8 square root of 0.64 square plus 0.48 square. So this is 0.8 meter long gate. So therefore, zero point 0.5 meter will be perpendicular to the screen or to the paper or your viewing direction. So for the solution, let's have the pressure at A, pressure at B. Then we have the trapezoidal pressure diagram on the gate. Let's divide this into two parts as shown. And the length is zero point 0.8. Let's call that F1, and the distance of F1 from A is zero point 0.8 over 3. F2 distance from A is 2 times zero point 0.8 over 3 or 1.6 over 3. Distance of F1 is zero point 0.8 over 3. So pressure at A is specific weight of water times 0.45. Then that's the tension. Let's call this angle theta. So pressure at A is 9.31 times 0.45. It is equal to 4.4145 kilopascals. Pressure at B is 9.81 times quantity 0.45 plus 0.48, the depth, and it is equal to 9.1233 kilopascals. And F1 is volume of pressure diagram, 1 half of 4.4145 kilopascals, height 0.8, and perpendicular to the board 0.5. So area of this triangle is this triangle here, then perpendicular to the board this value, perpendicular to the board is 0.5 meters, so 0.8829 kilonewtons. F2 is 1 half of 9.1233 kilopascals times height 0.8 times zero point 0.5 perpendicular to the board 1.8247 kilonewtons. Then tangent of theta is equal to 0.27 plus 0.45 plus 0.48, 1.2 divided by 0.64. So theta is equal to 61.928 degrees. Then we sum up moments about A equals 0. So T sine clockwise positive, T sine 61.928 degrees. The moment arm is 0.64. Then the horizontal component is counterclockwise, so minus T cosine 61.928 degrees times moment arm 0.48 minus F1, which is 0.8829 times zero point 0.8 over 3, then minus F2 1.8247 times 1.6 over 3 equals 0. Solving for T, which is the only unknown in this equation, so T is equal to 3.567 kilonewtons. Level 77. A prismatically shaped gate placed at the end of a freshwater channel is supported by a pin and bracket at A and rests on a frictionless support at B. The pin is located at a distance h equals 0.1 meter below the center of gravity C of the gate. Determine the depth of water D for which the gate will open. So take note that C is the center of gravity. It is where the weight of this prismatic uh, triangular wedge acts, the weight acts there. And since C and A are aligned, the moment of the weight of the gate about A will be 0. So let's have the solution. So let's have the division here so that we can have weight of water and horizontal force, which is equal to the volume of the pressure diagram on this side. So let's call the length of this as x. It is definitely less than zero point 0.4, and let's have d less than 0.75 assumption. So this is the pressure diagram. The pressure here is 9.81 times d, and F is acting 1/3 of d. From the bottom, F is equal to the volume of pressure diagram. And this is d over 3. And we have weight 1 uh, equal to specific weight of water times volume of this triangular wedge. This is area of the triangle times width perpendicular to the board. And let's just call it d later, or you can assume 1. So this distance is 1/3 of x, and we have weight of the gate which passes through C and through A. So these are the expected reaction AY upward and AX to the left. So this is point 1 given. Since this is triangular, the distance of C from the bottom is 1/3 of 0.75. So since this is already 0.10, the distance of this P from the bottom is 0.25 minus 0.1, where 0.25 is 1/3 of 0.75 because this is the center of gravity of the gate and this is triangular. So therefore the distance from C to the bottom is 0.25. Since h is given 0.1, therefore this is 0.15, that one. So this distance, on the other hand, is 2/3 of 0.4. 2/3 of 0.4 is uh, zero point 0.8 over 3. So when the gate will be about to open, there will be no reaction at B. It will pivot. So there will be no reaction at B when the gate is about to open. So take note, that's the condition. By similar triangles, x as to d equals 0.4, because this triangle here is identical or similar to this, not identical but similar to this triangle. So base x as to depth d equals base 0.4 as to depth 0.75. So x is equal to 8 over 15 of d. So F is volume of pressure diagram 1/2 of 9.81 d times perpendicular to the board. Let's have 1 meter, or you can call this d if you want, but for simplicity let's just call it 1. So 4.905 d square, W1 is 9.81 times 1/2 of x times d times 1. So that's 4.905 x, which is 8 over 15 d times d, so 2.616 d squared. Then since weight is not important because its moment about A is 0, so let's have summation of moment about A equals 0. So F times d over 3 minus 0.15. Take note, we sum up moment about d. So the moment arm of F is d over 3 minus 0.15. Then since that's clockwise, then moment of weight 1 is counterclockwise, so minus weight 1, and this distance is zero point 0.8 over 3 minus x over 3. So substitute the value of f, 4.905 d squared quantity d over 3 minus 0.15 equals w1 2.616 d squared, then factor out 3 in the denominator, 3, so we have zero point 0.8 minus x, and x is 8 over 15d. So next we cancel d squared and distribute. 4.905 d over 3 is 1.635d, then 4.905 times 0.15, negative 0.73575. Then here, 2.616 over 3 times 0.8, 0.6976. Then 2.616 over 3 times 8 over 15, negative, so negative 872 over 1875d. So take note, in this equation, only d is the unknown, so we can solve for d. D is equal to 0.6825 meter. Level 78, a 4 by 2 feet gate is hinged at A and is held in position by rod CD. NB rests against a spring whose constant is 828 pounds per foot. The spring is undeformed when the gate is vertical. Assuming that the force exerted by rod CD on the gate remains horizontal, determine the minimum depth of water D for which the bottom B of the gate will move to the end of the cylindrical portion of the floor. So this is the cylindrical portion of the floor. The condition is to determine the depth D for which the bottom B will move to the end of the cylindrical portion of the floor. So at this position here. And as stated here, spring remains, the spring is originally vertical. And we have to assume that the force exerted by rod CD remains horizontal. So if that's the case, the distance of CD is always 3 feet from A, vertical distance. So let's draw the gate that is now rotated so that B is now moved in this position, but the length or height of the gate remains 4 feet as shown. So this is the depth. This is now the rotated gate when the bottom moves in this cylindrical portion, so 2 feet horizontally. Then let's call the theta. This is also theta. Then cosine of theta is 2 feet divided by 4, because this is 4 hypotenuse. So theta therefore is equal to 60 degrees. So that this is d minus 4, and let's call this delta y. Delta y is equal to 4 feet minus 4 sine of theta. So from here to here, 4 sine theta. From A to B, 4 feet. So 4 feet minus hypotenuse 4 feet sine of theta, this distance. So delta y is equal to 0.5359 feet. So that the distance from, vertical distance from water surface to this end of the gate is d minus delta y, d minus 0.5359. So this is the pressure diagram. We have P1, P2. Let's divide this into two triangles as shown. And this distance can be solved by similar triangles again. Call that delta S. So delta S as to 3 equals 2 as to 4 sine of 60. So again, delta S as to 3 feet equals 2 feet, and this vertical distance is 4 sine of theta, or 4 sine 60. Delta S therefore is equal to square root of 3 feet, so that Fs, which is spring constant 828 pounds per foot, times square root of 3 feet. So it is 828 times square root of 3 pounds, the force in the spring. So let's have pressure 1, 62.4 specific weight of water in the system times vertical distance d minus 4. Pressure at 2 is 62.4 times quantity d minus delta y, d minus 0.5359. That's P sub 2. So let's call that F1, and the distance from A, from the hinge, is 1/3 of the height or 1/3 of the length of the gate, which is 4 feet, so 4/3. And on the bigger pressure diagram, triangular pressure diagram, its distance from A is 2/3 of 4 or 8/3 as shown. So F1 is equal to volume of pressure diagram 1/2 of P1 62.4 quantity D minus 4 times 4 feet, then times perpendicular to the board 2 feet, because we have 4 by 2 feet, so this is already 4, so that means 2 feet is the width perpendicular to the board, width of the gate perpendicular to the board. Simplifying, F1 is 249.6 quantity D minus 4 pounds. F2 is 1/2 of P2 62.4 times quantity D minus 0.5359 times length 4 feet times perpendicular to the board dimension 2 feet. Simplifying, F2 is 249.6 quantity D minus 0.5359. Then summation of moment about A equals 0. F1 times 4/3 plus F2 times 8/3 or equals Fs times 3 feet. Substitute the value of F1, which is 249.6 quantity D minus 4 times 4/3 plus F2 249.6 quantity D minus 0.5359 times 8/3 equals 828 square root of 3 times 3. So multiply everything by 3 and divide by 249.6. So we have D minus 4 times 4 plus quantity D minus 0.5359 times 8 equals 51.712. So 4D plus 8D is 12D, then 51.712 plus 4 times 4, then plus 8 times 0.5359. What that would be the value at the right side. In the left side, it is 4D plus 8D, so 12D, and the right side is 72. 51.712 plus 16, 4 times 4, then plus 0.5359 times 8, so that's 72. Solving for D, D is equal to 6 feet, and in the figure, D is, it is assumed that D is greater than 4 feet, since D is indeed greater than 4 feet, so that's the answer, 6 feet. Level 79. A long trough is supported by a continuous hinge along its lower edge and by a series of horizontal cables attached to its upper edge. Determine the tension in each of the cables at a time when the trough is completely full of water. Here is the given figure, and the tributary portion width is 20 inches. So if we isolate this part, and the section is quarter circular, radius 24 inches divided by 12, so 2 feet. So for the solution, let's have the quarter circular arc. Remember that perpendicular to the screen, it is 20 inches or 20 over 12 over 20 over 12 feet. So the pressure diagram is triangular as shown. Let's call the tension T. We are asked to solve for T. That's the pressure diagram, and the pressure at the bottom is 62.4 specific weight of water times 2 feet as shown. So F is equal to the volume of this pressure diagram, and it is acting 1/3 of 2 feet from the bottom A. So that's 2/3. Then we have the weight equivalent to this quarter circular arc. So specific weight of water times volume, that's W. The distance of W from A is the centroid of a quarter circle from A, which is 4r over 3 pi, or 4 times 2 over 3 pi. But by principle, if we have a circular arc, the component forces can be replaced by a single force, which is the resultant, and the resultant passes through the center of this circular arc. So here, so meaning we can move the components along the line of action of the resultant, which is here, so that the weight is no longer important. So F is the volume of this pressure diagram, 1/2 of 62.4 times 4 times height 2 feet, then perpendicular to the board 20 inches divided by 12 to make it fit. So F is 208 pounds. So as I said, we can move the components F and W because by principle the resultant of these two passes through the center of this circular arc, quarter circular arc, which is here. So let's remove them and put the components transferred here so that the weight W has no moment about A. So summation moment about A equals 0, F times radius minus T times radius equals 0. So that means tension equals F. But we have already solved F, 208 pounds. Therefore, the tension is 208 pounds. So that's the answer, and that's the solution. Now, if you cannot think of moving the component forces along its line of action, which by principle passes through the center of the circular arc, if you cannot think of that, then let's continue by solving W, and we sum up moments about A and verify that the answer is still 208 pounds. So that's it for the second solution. W is specific weight of water times volume, which is area of quarter circle, pi over 4 radius square, times perpendicular to the board dimension 20 over 12. So weight is 62.4 times pi over 4 times 2 square times 20 over 12. So simplifying, that weight is 104 pi pounds. Then, because the distance is given, summation moment about A equals 0. So T times 2, then equals, so that's counterclockwise moment equals clockwise moment. So let's put the forces back to their position, so here and here, so don't mind that. So equals F, which is 208 moment arm 2/3, plus W, which is 104 pi pounds moment arm 4 times 2 over 3 pi. So cancel pi and simplify, solve for T. The value of T is the same, 208 pounds. So that's it for this problem. Level 80 is the last problem. The square gate AB is held in the position shown by hinges along its top edge A and by shear pin at B. For a depth of water D 3.5 feet, determine the force exerted on the gate by the shear pin. So here is the position of the shear pin. Let's draw the free body diagram of this part. We're looking for the force in the shear pin when the depth is 3.5 feet. So since everything is known, then we can compute the pressure at A and at B. Then let's divide that pressure diagram into two parts so that we can compute the equivalent forces which represent the volume of the pressure diagram. And the width perpendicular to the board, the gate is square. So therefore, if it is 1.8 high, 1.8, so perpendicular to the board, 1.8 feet also. So 3.5 minus 1.8 is 1.7. So therefore, if this is the gate, so 3.5 minus 1.8, the pressure at A is Specific weight of water 62.4 times 1.7, because 3.5 minus 1.8 is 1.7, while the vertical distance from water surface to B is 3.5 minus this delta y here. So that's 1.7, 1.8. This angle is 60 degrees because this is 30 from the vertical, so 60 degrees from the horizontal, and call this delta y. And this is the force, shear force in the shear pin, which is the required force. So delta y is 1.8 minus 1.8 sine of 60. So 1.8 minus 1.8 sine of 60 degrees is equal to 0.24115 of a foot. So this is the pressure diagram. Let's divide that into two triangular diagrams, and let's call that equivalent force in this triangular pressure diagram, the smaller one, as F1, and its moment arm from A is 1/3 of 1.8, so 0.6 feet, 0.6 of a foot rather. Then we have F2, the distance is 2/3 of 1.8 or 1.2 feet as shown in the figure. So P1 is equal to 62.4 times 1.7, so that's 106.08 pounds per square foot. P sub 2 is 62.4 times quantity 3.5 minus delta y. So 62.4 times quantity 3.5 minus 0.24115. So that's 203.35 pounds per square foot. So from there we can solve for F1. F1 is 1/2 of P1 times 1.8 times 1.8 because it is a square gate. So 171.85 pounds. F2 is 1/2 of pressure 2, 203.35 times 1.8, then perpendicular to the board 1.8 also. So 329.43 pounds. Then finally summation moment about A equals 0. So FB, force in the shear pin, times 1.8 equals F1, which is F1 times 0.6 plus F2 times 1.2. Substituting the values of F1 and F2, so FB times 1.8 equals 171.85 times 0.6 plus 329.43 times 1.2. So it is FB that is left here. Solving for FB, FB is 276.9 pounds. So that's the last, and I hope that uh, the principle on hydrostatic pressure is presented here, and I hope that you were able to follow the solutions. The forces are just equivalent to the volume of pressure diagram, which can be easily computed as area of the pressure diagram times width perpendicular to the board for rectangular gates. For non-rectangular gates, you have to apply integration. And as I said, this topic here is well discussed in the course Hydraulics or Fluid Mechanics and